So our first question. Our first question asked about which has the smallest electronegativity. Hopefully, there we go. So we're looking at these four in green right here. And I got a few answers. Does anybody want to say their answer out loud? What did they take a guess as to which one has the smallest electronegativity?
Wait, no. Francium.
All right, I heard francium. Does anybody agree or disagree with francium? Does anybody have a different answer? Does everybody like that one?
I agree.
You agree? I got a thumbs up. We got lots of agreeing. All right. And I'm liking that answer, but there's one element who does beat out francium. So can you guys remind me what electronegativity means?
It's stable. Wait. It's the tendency for atoms to share electrons, their valence electrons.
So not just share, but they're going to be pulling on those shared pair of electrons. So it's the tendency for an atom to pull on a shared pair of electrons. So francium is going to have a huge care that it gets rid of it. It's going to want to get rid of that electron. It doesn't like it, so it's going to get rid of it, which means it's going to have the tiniest electronegativity except for one whole column. Anybody take a guess as to what column is going to have a smaller electronegativity?
The noble gases.
The noble gases, and that's because, do they want to share electrons?
No,
because they don't have a want to share electrons. So what do we think their electronegativities are going to be?
None.
None. These guys over here have an electronegativity of 0. They don't share their electrons with anybody, which means they are going to have the smallest electronegativity of 0. So francium would have the next smallest. Which one is the largest electronegativity then? Just if you had to guess.
Fluorine?
Fluorine has the largest electronegativity on the periodic table, and its electronegativity is about 3.98 or 4, depending on which periodic table you look at and which electronegativity you're looking at. But it's about 4. It's got the highest electronegativity or the largest pull on a shared pair of electrons. The next question asked about the electron configuration of molybdenum. So it doesn't go away. But what is that electron configuration of molybdenum? I got a few answers. Anybody want to say theirs out loud? You can do shorthand, longhand, whatever you want. All right. How about I go through it? So we have our 1s2. As we cross those out, 2s2, cross those out, 2p6, we cross those out, 3s2, we cross those out, 3p6, we're going to cross these out, 4s2, cross those out, 3d10, cross these out, 4p6, we're crossing these out. 5s2, we cross these out, and then 4d4 would be to here. Is everybody okay with that so far? Because we're going to have to change a little bit because this isn't perfect. And it's not perfect because if we think about it in orbital notation form, I'm just going to write it in shorthand. So I'm going to start with krypton just to make my life a little bit easier. So krypton, and then we have our 5s, then we have 4d. So right now we have it drawn like this. So then this is completely filled, and then this one is almost got halfway filled. It still has that one missing. And so that one missing is going to steal that electron from 5s and going to pull it onto 4d. because it'd rather fill half of 4D and half of 5s than have 5s completely filled and be missing one of the orbitals from having an electron in 4D. So it's going to be one of our special ones that's going to be 4D5 and 5s1. So we're going to change this to a 1 and this to a 5. Because it'd rather have 5 in the D and 1 in S than 2 in S and only 4 in our D, and leave this one blank. It wants that one filled. Can anybody take a guess, if we had to guess from the periodic table, any other ones that might be in our special case besides just molybdenum? Any other elements you can think of?
Copper.
Copper, all right. Yes, that is a special case because it's got 9. It'd rather fill all of 3D than have all of 4s fill, because 3D is lower than 4s, which means it wants to fill that lower energy level first. If it's so close, it wants to just get that last one in 3D rather than 4s. So copper is a special case where it's going to be 4s1, 3D10. Any other ones? There are 5.
Chromium.
Chromium, good. There are 2 more. Take a guess. Anywhere on the periodic table.
Silver.
Silver, all right. There's one more.
Rhenium?
Which one did you say?
Rhenium?
Rhenium. Where's rhenium? Where is that?
It's next to tungsten.
75.
75.
You said 75? Oh. Not rhenium. Just because that one's going to actually be 5. Because remember, there are 15 down here, which means this one actually belongs in the 5D block. And then this one belongs in 6D. And then tungsten's not going to do it just because of that 4F is going to cause it not to steal 6S's because of 4F. But there is one more that 4F doesn't stop. Which one would that be? Which one do we think? If we look at the pattern, ignoring tungsten is one of our patterns that it excludes. What's the other one going to be?
The gold.
Gold, perfect. Those are going to be our 5 that don't follow our normal pattern. They're going to steal one from the S so that they can have their D block filled rather than have their S block filled. Any questions on that? And then the last question from our bell ringer was about ionization energy. What does it mean if it has a small ionization energy?
That it doesn't require a lot of energy to remove an electron.
Exactly. It doesn't require a lot of energy to remove an electron. All right. So one more thing I want to do before I let you guys go ahead and work on your reviews is I want to go through that formative from yesterday. So if we look at the formative from yesterday from your Canvas page, there were, what was there, 13 questions? So we're going to go through those 13 questions. The first one being, which of the following elements has the highest reactivity? And so we're looking on our periodic table, the ones that have the closest to a full valence shell. So this one has 7 valence electrons. Silicon has 4 valence electrons, 3 valence electrons, and 2 valence electrons. So the one that's closest would be the one that gains or loses the least amount of electrons. And so that one's going to be chlorine here, because it's going to only need 1 valence electron to get to its full or its stable 8 valence electrons, have a full valence shell. The next one we're looking at, it says which is the highest reactivity. So we have lithium, which has 1 valence electron, rubidium, which has 1 valence electron, barium, which has 2 valence electrons, and beryllium, which has 2 valence electrons. So now we have to talk about the fact that one, whichever one has the least amount of valence electrons, and two, which one is going to have the largest ion or the smallest ionization energy. Because rubidium and lithium both have 1 valence electron, but rubidium is going to have a smaller ionization energy, meaning that it's easier to remove rubidium's valence electron than it is to remove lithium's valence electron, meaning that it's going to react faster with rubidium than it would with lithium. Any questions on those two? All right. Then number 3 says, what will the charge of an ion of nitrogen form? And that is going to mean that if it has 5 valence electrons and it wants to get to 8, the quickest way to 8 is to gain 3 more or have a -3 charge, because it's gaining 3 negative charges. What charge will the ion of barium form? Barium has 2 valence electrons. The easiest way for it to get to 8 would be to lose those 2 valence electrons or have a +2 charge. Which of the following elements is going to be the most reactive here? We have iodine, which has 7 valence electrons, antimony, which has 5 valence electrons, aluminum, which has 3 valence electrons, and fluorine, which also has 7 valence electrons. So now it's going to be between iodine and fluorine because they both have 7 valence electrons. They're the closest to 8. So now we have to determine which one is going to attract electrons more, because they're trying to pull in 1 more electron. It's going to be the one where the protons and the electrons are closer together, so the smaller atom, or fluorine, which has the larger electronegativity. So it's going to pull those electrons in closer. Number 6, what will the charge for selenium form? So selenium has 6 valence electrons, which means it has 2 away from having 8 valence electrons. So it's going to gain 2 and have a -2 charge. Elements that generally form a positive charge are going to be the ones that are losing valence electrons. And so those are going to be the ones on the left side of our periodic table, or our metals, because they're going to lose valence electrons. Number 8, in a bond between lithium ions and chlorine ions, what would happen? So for this one, we know that our lithium wants to lose electrons and our chlorine wants to gain electrons. So our lithium would give 1 valence electron to chlorine. And that one's more just like a foreshadowing to our next unit on bonding, where that's going to be happening, and we should see that. That one was more of, can you think about that in terms of what would those ions actually be doing? Not just losing the electron or gaining electrons, but where are they coming from? So that's not on your test for this unit. So if you didn't get that one right, it's okay. Which of the following elements would have the highest reactivity? So we look at oxygen, which has 6 valence electrons, polonium, which has 6 valence electrons, antimony, which has 6 valence electrons, and sulfur, which has 6 valence electrons. So now they each want to gain 2 valence electrons to have a full valence shell, to have 8 valence electrons, which means the one that's going to pull the most electrons in, or have the strongest pull between its protons and electrons, will have the highest reactivity. And in this case, it will be oxygen, which is the smallest atom or the smallest atomic radius or the largest electronegativity, meaning that it pulls its electrons in the closest. Which of the following metals will be the most reactive? We have copper, calcium, potassium, and francium. So copper is going to have 2 valence electrons, calcium has 2 valence electrons, potassium has 1 valence electron, francium has 1 valence electron. So it's between potassium and francium, which one is going to have more reactivity, because they both have 1 valence electron, and it's going to be the one with the largest atomic radius or the smallest ionization energy, willing to give away its electron the most, which is going to be francium. Then number 11 says rank the following in order of decreasing electronegativity. So we have sulfur, arsenic, cadmium, and platinum. So sulfur, arsenic, cadmium, and platinum. So sulfur is going to have the highest electronegativity. It is going to be the smallest. So it's going to pull its electrons in the tightest. Then it's going to be arsenic, and then cadmium, and then platinum. So then it says use the principles discussed. You can use electron configuration 2 to explain the trend of the electronegativity across the period and groups of the periodic table. So if you want to include pictures, if you wanted to draw Bohr models or Lewis dot structures, you can, but you should be talking about the Coulombic attraction between the protons and the electrons, and the fact that the more protons and the more attraction there is toward the nucleus. Then also explain how as you go down the periodic table, you're gaining orbitals. So your electrons are getting farther from the nucleus. So you're going to get larger as you go down, and you're going to get smaller as you go across. And so the smaller you are, the more pull you have on the electrons, which means that you're going to also pull in shared pair of electrons. And then the last question says, explain the octet rule of chemistry or the role that it plays in reactivity. So the octet rule, again, is that all elements want to have 8 valence electrons, and they're going to do that by bonding or forming ions. And the octet rule plays a giant role in reactivity because we only react with other elements because we want to gain or lose electrons to have a full valence shell. So they're only reacting with other elements so that they can have their 8 valence electrons. Are there any questions on that formative? I know I just went through a lot. All right. So then the last thing you guys are going to be doing is there is a review for your summative on Canvas. The review goes through the trends and then the explanation aspect, and then reminding you guys about electron configuration and some practice with that, because there are going to be a couple multiple choice problems with electron configuration. And then the other worksheet that is on your Canvas page is another practice worksheet. It is not required by any means. It's just more practice. Does not ever have to be turned in, but there's another practice on Canvas that goes through, again, just electron configuration, Lewis dot structures, or octet rule, talking about reactivity and how reactivity and those trends are interacting with one another. So there's also this one, and then this answer key and the other answer key will be on Canvas in your modules right after their assignments. So you should see the answer keys show up later today right underneath the trends unit review and the trends and reactivity practice. So both of those answer keys will be on your modules